Next, we're going to turn our attention to related subjects with two papers on the applications of space solar power technologies for in-space infrastructure, which in themselves would be extremely important for the deployment of ambitious large space systems such as solar power satellites. And the first presentation will be from Joe Howell from the Marshall Space Flight Center. Joe was for a number of years the project lead for NASA's space solar power technology efforts. Joe.
Okay, thank you, John.
Use the mic.
You have the mic.
I stole the mic from you right here.
Okay, is that better? Good. What I'm going to talk about here is things that are a little bit more, oops.
Sorry about that.
Okay. Some of the things we've done a little bit more recent than the earlier space solar power studies, and talk some about modular systems and reusable systems and so forth. And I want to also acknowledge contributors to the presentation here, Connie Carrington, Neville Marswell at JPL, and John Mankins, and several others have also had inputs to this presentation here. The challenge here is the really affordability. And one of the central barriers that we have against more ambitious and affordable operations in space beyond LEO lies in the inability to pre-position consumables such as propellants and spare parts and so forth. So as long as we're not able to locally repair and refuel these high value or high cost assets in space, this ability of affordability is really not achievable. So the challenge here in planning a wide range of potential future missions here is to look at important things like the high value missions, the human exploration beyond LEO, to look at large space systems, defense, security systems, and future space industries such as the large multi-payload geo platforms, space solar power systems, and so forth. So from a notional example, and can't quite see that, but anyway, the operations of human lunar missions. If we look at, for example, a large-scale permanently based on the moon, and we're doing 3 or 4 missions a year to the moon and changing out crews every 120 to 90 days. Looking at the mission scenarios based on Apollo era concepts, based upgraded technologies to current technologies, but we're still looking at cost of hardware for these the missions and the operations in the range of 2.4 billion to 3.1 billion in current year dollars. And looking at the transportation parts of this for LEO, if we assume the shuttle derived expendable systems, a couple of heavy lifts, and a couple of CEV type launch vehicles, in the $500 million to $1 billion range missions, the LEO cost of consumable systems for 3 or 4 missions a year here, and we're assuming the EELV for the expendable launch vehicles. And in space, we're talking about a couple of in-space vehicles here, around 10,000 kilograms, and a typical cost of like $50,000 per kilogram. Then we're talking about another $500 million per mission. In addition to that, then we're talking about excursion transportation systems then of 10,000 to 20,000 kilograms. Here again, about the same rate of cost per kilogram for these. We're talking about another $750 million per mission. And the operations that go along with this, assuming shuttle or upgraded station type operations with about 20,000 personnel to do this over a year. And if we're doing 3 to 4 missions a year, we're talking about $500 million to $2/3 billion per mission for these type of operations. So in summary here, if we're talking about 3 to 4 missions a year, we're talking about like $7 billion to $11 billion dollars per year. And this is there's other additional costs, the crew systems and communications and other surface systems that would go along with this. So we're looking at, in order to do affordable or sustainable, ambitious space operations, we're going to have drastically lower cost way of doing business here. Potential solutions here. Let's look at 4 key technology areas here. One is the lower cost Earth to orbit transportation systems. We look at enabling transportation systems here, launchers that would be common against government and or commercial sectors for doing ETO, and even transitioning then onto reusable systems eventually in the future. Another is the highly autonomous assembly, servicing, and maintenance of modular systems for both space and planetary operations. The affordability of and timely preposition of fuels like propellant depots and other materials that would need for servicing missions in space and on the surface of the moon, and reusability and highly reliable, high-energy space transportation systems for both the lunar and excursion vehicle systems. To look at the expendability of systems, if we look at the Apollo-type updated system here, we're talking about very high-cost, mission high-cost systems here. To get down to affordability and sustainability approaches, we need to be in a box over in this region here. And basically what this chart is telling us is we need to be to a low percentage of expendable systems to get into a box like that. If we look at the number of systems, if we want to look at why doing modular systems, if we look at the number of systems that are produced in the system based on historic data, we see that the cost of these systems comes down as the number of systems goes up. So this curve here is the number of modules in a system, and this is a cost basically per module type system. So modular systems tend to reduce the cost per kilogram of the systems. Another thing is the why autonomous and intelligent systems is the higher number of people that's involved in the operations is going to drive the cost up. So to get in a box, a range of interest here for a low number of missions per year, need to have the number of people involved in these operations down. So intelligent systems is critical to reducing cost of the operations. Pre-deployment of logistics such as propellants and so forth. If we look at what can be delivered for different locations in terms of if we have pre-deployed propellants versus not having pre-deployed propellants, there's a big range in the capabilities of doing that. And this is just the payload of having the things like a depot versus not having them. It doesn't take into account getting them up there. This is looking now at why the refueling and high energy systems are both required. If we look at the Apollo type expendable systems here and like a highly reusable electric propulsion system, high efficiency system here. It looks like, hey, the amount of mass to low Earth orbit is about the same, but you have to remember, these are reusable systems here. These were expendable systems here, which extremely drive the cost up. Over here now is reusable chemical systems, which requires a lot more propellant to orbit than the higher efficiency solar electric system. So both the refueling and the high energy electric propulsion systems are needed for reducing costs. This is just examples of some single unit, non-modular systems, solar electric system here based on solar panels and electric thrusters. This is another configuration called a batwing array with electric thruster SEPs, but these are single units, non-modular systems. An example of a modular system would be each one of these systems here has your propulsion systems and your solar electric power generation system are modules, and these can be brought up in many modules to produce a SEPs type of vehicle in a modular form. So some of the key technology challenges here that supports the space solar power systems, as well as many other type of operations for space beyond LEO, is the supervised and eventually autonomous systems, the self-adaptive modular systems, space assembly, and maintenance and servicing. And the reason I've got some of these highlighted here is because we have been working more recently in some of the things that are very important to the early try to advance these activities here. All of these are important, but we've been really pushing on these ones that have got highlighted here in the last couple of years. Others is the highly fuel efficient, reliable, restartable propulsion systems here, both electric and chemical, and restartable chemical engines are important for the more critical missions such as crew missions. High energy propellants are important, particularly for depots to store the liquid oxygen, liquid hydrogen propellants. And long-term storage and management of the cryo systems are key, which is part of the depot activity. And the high power, low mass generation using systems that are generating power at a higher voltages and reducing the power management and distribution systems. Looking at this example here for benefits related to both the refueling and the high energy, if we look at reusable systems, you got an injection stage here going to the different locations, different missions. The difference between the refueling over here and the non-refueling is very obvious here. And if you look at then the higher efficiency systems, such as a SEP stage, there is some gain from refueling, but it's not near as pronounced as it is for the lower ISP chemical systems. And this right here is concepts relating to the solar clipper modular transfer system that can produce transportation from a low Earth orbit to GEO for a space solar power concept that was generated that Seth and talked about a minute ago. This is an integrated symmetrical concept. There's a lot of modularity in this system in reflectors, some modularity in the photovoltaic receivers here, and then the rectenna that would be our antenna that would be beaming down to a rectenna on the ground. The lower right-hand corner here is the modular solar electric SEP system here for going beyond GEO on out to Mars and so forth. So, in order to do these ambitious space operations, particularly beyond the LEO, we must have more affordable systems to be more sustainable in our operations. The modular self-adaptive high energy systems is one of the important alternative approaches to achieving these goals of reduced operation cost. Key technology challenges, however, have to be addressed and developed in order to apply these technologies to the space applications. And in the near term, some of these large-scale technology flight demos that need to be done here could be achieved in the next 5 years or so for both component technologies and system functionality. And I think that's the end of mine, John. Yes.
How similar your thinking and my thinking is, not even considering the production, just the whole concept of the reusable and the depots and everything else. You're basically singing my song.
Yes. Any other questions?
Some of your mathematical analysis suggests that a better metric than a lot of presentations that I've seen in these conferences, initial mass in LEO is this, or amount of cargo, that a certain vehicle can take to orbit is that. But if you take into account reusability and modularity, I think the advantages are more apparent if you use some new metrics. The example I was thinking of is the pound of Saturn V can carry, how many kilograms of cargo versus space shuttle. But if you look at how many kilograms of space shuttle, how many kilograms of cargo a kilogram of space shuttle can carry over its operational lifetime, then the advantage of reusability is more apparent. So I noticed that you had the beginnings of a recasting of the metrics in which the advantages become more apparent. So I thought that was
While Joe is bringing up the next talk, which will be offered by Mark Kennedy from Boeing rather than John Fikes, who will be with us today. We'll hope for the best. I'll just note that in one of Joe's charts, he mentioned the various benefits from these kinds of systems. One of the central points was the idea that the same solar electric propulsion system that you could use to deliver large amounts of cargo to a place like low lunar orbit, you could also use to deliver large elements of future satellites such as solar power satellites to geostationary Earth orbit. And the exact same system can be quite useful to deliver many tens of tons to Mars orbit by using a combination of a set stage to spiral out of low Earth orbit and then a high energy chemical stage for the final kick to Mars. So one of the notions here was that of having a common set of building blocks that lets you implement a wide variety of different applications.